Okay, so in this example we're going to be looking at solving a second order linear differential equation that's related to an application. And the application of that is that of a buoyant object floating in a tank of water. The x here denotes the displacement of the object from its rest position. The delta incorporates some kind of damping effect. The k squared involves gravitational forces and other fluid properties. And this buoyant object has a force applied to it of a form F times cos of k of t, so this force oscillates over time and is applied directly up and down, very similar to the examples we've seen in lectures. So that's our differential equation, and it's going to be solved subject to some initial data, namely that the displacement and the velocity of the object, that is x and dx by dt, are both 0 at time t equals 0. We're also given some additional information that k is greater than delta, and both of these parameters are positive. So what we've got is a second order linear differential equation, and we're going to solve it using the standard methods. Namely, we're going to try and figure out the complementary function and then get a particular integral, and then once we've got that general solution we're going to determine a particular solution by applying the given initial data. So let's start off trying to find the complementary function. We can do this by working out the auxiliary equation. So all we have to do here is to replace derivatives of x with powers of m. So, for example, we have the second derivative of x with respect to t, that's going to get replaced by an m squared. Our dx by dt, that's going to get replaced by an m, and so on. So our auxiliary equation is m squared plus 2 times delta times m plus k squared is equal to 0. So this is a quadratic equation that we can solve using a formula. So we substitute in into the formula. We see that m is minus 2 delta plus minus the square root of 4 delta squared minus 4k squared all over 2. So inside the square root sign we've got a common factor of 4 that we can pull outside the square root, which manifests itself as a 2, and now we have a common factor of 2 top and bottom of a fraction that can cancel. Furthermore, this square root contains a d squared minus k squared. We're told that k is larger than d, so this means that delta squared minus k squared is negative. So let's rewrite delta squared minus k squared as minus k squared minus delta squared. So this means now the term in brackets, the k squared minus delta squared, is positive. So our roots of our auxiliary equation are minus delta plus minus the square root of minus 1 times k squared minus delta squared. Well, of course, the square root of minus 1 is the same as that complex number I that we've met quite a few times now. So the roots of our auxiliary equation must be minus delta plus minus I times the square root of k squared minus delta squared. Notice the k squared minus delta squared is positive, so the square root here is a real number. So we can form a complementary function now by noting that the roots of our auxiliary equation are complex conjugate pairs. The real part, circled here, is minus delta. The imaginary part, circled here, is the square root of k squared minus delta squared. So this means we can form a complementary function being e to the minus delta t, all multiplied by a sine of the imaginary part of our roots times t, plus b times cosine, the imaginary part of our roots, times t. So that's our complementary function. We now have to work out a particular integral, and this we do by looking at the right-hand side of our second order equation. Well, the right-hand side is a function, a trigonometric function, whose argument is k times t. Let's note that this function does not feature in the complementary function we've just derived. So given this, let's try a particular integral of the form a times sine kt plus b times cosine kt. In other words, our particular integral is the general form of what's on the right hand side, and we're going to try and work out values for a and for b. We do this by substituting for p into our differential equation and comparing both sides. So our differential equation, it was a second order one, so we need to have the first and the second derivatives of p. So if we differentiate p, we get a times k times cos kt minus bk sine kt, and differentiating p prime again to get p double prime is minus ak squared sine kt minus bk squared cos kt. So let's now substitute p and its derivatives into our differential equation. So a differential equation, as we can see, is p double prime plus 2 times delta times p prime plus k squared times p. So this gives us minus ak squared sine kt minus bk squared cos kt, and so on all the way through. Now principally we've got lots of terms here involving sine and involving cosine with argument kt, so let's group these together. And we can do this, and we note that the terms involving the ak squareds cancel. And so we see that p double prime plus 2 delta p prime plus k squared p must be 2 delta ak cos kt minus 2 delta bk sine kt. So this we now compare to the right hand side of our differential equation, which was f times cosine of kt. And by comparing the left and right hand sides of this equation, we can figure out values for little a and for little b. So let's compare terms involving cosine of kt. Well, on the left hand side we've got 2 times delta times a times k. On the right hand side we've got an f. This means that a has got to be f over 2 delta k. Now let's compare terms involving sine of kt. Well, on the left we've got minus 2 delta b times k lots of sine kt. On the right hand side we've got 0 lots of sine kt, so this of course means that b must be 0. And this of course means we can get a particular integral, which must be f over 2 delta k times sine kt. That was our a times sine kt plus b times cosine kt that we noted earlier. So we can get a general solution of our equation by adding together the complementary function and a particular integral. So this gives us the x shown here. Now let's apply the given initial data to work out the particular solution. Right, since x was 0 at time t equals 0, all we have to do is to replace t by 0 into the general solution above. Now let's notice that e to the minus delta t when t is 0 takes the value 1, and similarly the cosine of the square root of k squared minus delta squared of t also takes the value 1 when t is 0. Furthermore, the terms involving sine, circled here, will take value 0 when t is equal to 0. So replacing x by 0, replacing t by 0, we see that we have 0 is equal to 1 times 0 plus b plus 0. In other words, 0 is equal to b. Let's now apply the second part of initial data we're given, namely that dx by dt is 0 when t is 0. Well, to do this we've got to differentiate our x with respect to time, and let's do that by setting b to be 0, since we've worked that information out already. So we need to differentiate the x, general solution x, when b is equal to 0, and we see that our x involves a product of two functions, the e to the minus delta t and the a times the sine. Well, we've got that product of two functions, so we need to differentiate it using a product rule, and this we do on the line shown here. So now let's apply the given initial data that dx by dt is 0 when x is 0. So again we notice we have an e to the minus delta t and a couple of cosine terms actually, all is shown in red. Well, when t is 0, each of these terms circled red must take a value 1. Similarly, when t is equal to 0, the sine term circled here must take a value 0. So when we make those substitutions and set dx by dt to be 0, we see that we have 0 is equal to a times the square root of k squared minus delta squared plus f over 2d, and of course this rearranges to give capital A as minus f over 2 delta square root k squared minus delta squared. So we've now found a and b, which we can substitute into our general solution to get our particular solution. And if we rearrange this particular solution by pulling out a common factor of f over 2 times delta, we get our particular solution f over 2 delta times the terms in square brackets as shown here. And this was in fact the solution we had to obtain.